As our next speakers, we will hear from Firat and Simon on how to prevent floodings on river sides, a topic that's it's very current, very relevant, especially since we remember last year's Germany's flooding with catastrophic consequences. Now, Firat and Simon will tell us how to prevent such floodings using signals, acoustic signals actually. And I very much look forward to hearing your presentation, which is, by the way, their student project at FHNW at the University of Applied Sciences. So without further ado, Firat and Simon, thank you very much.
So, thank you. A warm welcome to our presentation about using acoustic signals to predict grain size of Bellow particles. First, the clicker is not working.
It was working before.
Oh, okay.
Just press
okay, thanks. Okay, first a quick introduction to the speakers. My name is Simon, and I'm currently studying Bachelor in Data Science in the last semester. My background is automation technician, and in my spare time you can find me in the mountains.
Also from my side, a warm welcome. My name is Firat, and I'm also studying data science with Simon together. We are in our last semester and we'll finish our study this summer. My background is kind of similar. I worked as a draftman for 5 years, and in my spare time you can find me on a basketball court or in a virtual environment.
Okay, so before we dive deeper into the subject matter, we need to first understand what is Bedload transport. So if anybody here heard of Bedload transport before, I would kindly ask you to raise your hand. Okay, not that many, but as expected actually, because it was the same for us before we started this project. So when we are talking about Bedload transport, then we are talking about these grains which are located on the river ground, and they have a lot of contact with the riverbed as they are transported through the river, as you can see on these curved arrows visualized. So now let's have a closer look on the risk and dangers which come along with Bedload transport. Therefore, we have two images which show the exact same location, which is located in Bondo, Switzerland. And what happened there is that a huge Bedload transport event damaged the local infrastructure. As we can see here, there are like damaged streets, pathways, as well as houses. And another like risk and danger which comes along with Bedload transport is more like a long-term event. We can see this on the image on the bottom, and this is the deformation of rivers. And this can be cautious for the river morphology and the surrounding vegetation, of course. And so if you ask yourself now if it's possible to measure such kind of Bedload transport, yes, it is possible. Therefore, our project partner, the WSL, developed 3 measuring systems, as you can see on the left image. There is the square pipe system, SDS, the Swiss plate geophone, SPG, and the third, the mini plate accelerometer, MPA. And on the left image, you can see them installed in the artificial flume, where they conduct controlled experiments to collect data. And for the SPG, we have also a picture how it looks like when it's installed in a Swiss in a mountain steam here. So to make it a little bit clear that how this process looks of the data collection in this artificial flume, we have this animation, but it looks like that it does not work. But actually, the grains would be put through the artificial flume there, and as they are impacting on the measuring on the sensor plate, they would like here produce these waveform signals on the bottom. But yeah, sadly, it's not visible.
So thank you very much. Now you saw how the data has been collected. Now let's move on to the implementation part. Normally this is animated, but I see it doesn't work really good, the presentation, so I try to explain it on this way. So as Simon mentioned, we have 3 different measuring systems, the MPA, SPS, and the SPG system, and from that we get raw signal packages. One example you can see on the top of the slide, there is a vibration when a grain hits a sensor, and this is the amplitude over a certain time. We have around 150,000 of this kind of raw signal packages. You can see on the front the pie chart, the distribution of the different systems, and we can clearly see that, for example, the SDS has the smallest amount of data points, and the reason for that is because it is the newest one. We have just data from the last year from the measuring system SPS, and the other one goes until 2018. So what we did now with the raw signal packages, we tried to make extraction to extract features with different methods. For example, a Fourier transformation is one of them. And then we got different amount of features. You can see here, for example, the MAB, this stands for the maximum absolute amplitude. And you can again see that there is a G01 and G02 for one exactly same feature. This stands for the sensor because this example is from the measuring system SPG, and the SPG has exactly 2 sensors in the artificial flume. So what we also have on the left side, you can see it, the size in millimeter. This is our target variable. This is what we want to predict. So now let's move on with the target variable, and let's see how the distribution look like. We can see that we have a strongly unbalanced data set here. That's not really ideal for us because we have a good amount of data points in the middle grain sizes, but for the biggest and especially for the smallest one, you can see we have just like 2 data points. That's literally nothing. So we can assume that we can't really predict them. What we also have here is a discrete distribution of the data set, which is also a handicap for us because in a real natural environment, the grain sizes would be continuous, so it wouldn't be categorical like this one. So now let's focus to the features. For that, we did a heat map where we compared all different features which we have to see if we have any strong correlation with each other. And we saw here that we have indeed a strong correlation between one feature with the different sensor types because as I told you, the SPG sensor, again here, from all the features, that it has 2 sensors, and if one grain hits one sensor, we got like a similar pattern for the other one, so we saw that they have a strong correlation with each other. So what we did, we tried to find different methods to reduce the amount of the features without losing any information. For that, we did an aggregation, and Simon will explain you later how that worked. So now let's take one feature. For that, we took the centered frequency. This is the weighted average of a Fourier transformation. And on the left side, on the histogram, we can observe that we have a bimodal distribution. You can see that on the 2 characteristics. And it's also important to know that a lot of features from us has a bimodal distribution like this. And if we compare it with the target variable, our grain size, we can see here a correlation that if the centered frequency is decreasing, that the grain size is increasing. So we can assume that this feature can be important for our model later. So now let's move on to a more exciting part in our project where we compare different models. You can see that on the graph, on the upper part, we have more the linear models, and on the lower part, there are more the tree-based models. And we compared these models with the R2 score. We chose the R2 score because it captures the relative errors really good and it is easy to understand. You can here also clearly see the gap between the linear and the tree-based models, and the reason for that, you saw that on the slide before, that we have a bimodal distribution, and everybody knows that linear model works better with normal distributed data set. And so what we did is also we tried different transformation, for example, a log transformation, to see how the linear models will change the performance. And indeed, they were better, but not so good as the tree-based model. And the tree-based model, on that, there was no difference without or with any transformation. So we decided to make any transformation on that data set. So you can see that the cat-boost regressor was slightly better at the end over all measuring systems, so we decided to move on with that cat-boost regressor and make further analysis and optimizations on that. A few words to the get-put regressor. It is a gradient-boosted tree algorithm, and it is really successful on Kaggle. And maybe it is really successful on Kaggle because it has good default parameters.
Okay, thanks, Firat, for these exploratory insights into our project. Let's move on to the pre-processing. Therefore, we applied 2 different models for each measuring system. First, we'll have a closer look on the simple model. The simple model only consisted of a data aggregation step, which we call here max feature aggregation, and we'll come back later on it because it was a very important part in our analysis. The goal of the simple model was to have a good transferability from the artificial flume to the field measurements. And then for the complex model, as you can see, it looks a little bit more complex than the actual pre-processing for the simple model. Here we have an additional extraction step from the raw data signals, as well as an additional data aggregation step, which here is the aggregation over equal sensors for one measuring system. The goal of the complex model was to have also a good transferability, but to lift the variance variance bias trade-off more towards higher variance and lower bias on the field measurements. So as I mentioned before, let's have a closer look now on the max aggregation. Therefore, we focus only on one measuring system, the MPA. And here we can see the amount of feature, which is 30, and we're able to reduce the amount of feature to only 13 features. So how did we do this? We have to say here that the measuring system MPA consists of 4 sensors which are located in parallel to each other as visible here. This is an image from the artificial flume, if you remember. And therefore, for each sensor, we have a feature denoted as M1 to M4 on the upper table. And we also got the feature map, MAB, which is the maximum absolute amplitude. So, and we assumed here that where the maximum absolute amplitude appeared, there the grain must have the impact on this sensor. So for this sample, we will take the feature for the sensor M2 as a representative for all other features for this example. So let's go a step further to the optimization of our model. Therefore, we used Optuna, which is a hyperparameter tuning framework written in Python. We optimized parameters from our model like iterations, learning rates, and so on. Then at each optimization iteration, we performed a 5-fold cross-validation with the optimization objective of the R2, the mean R2 score of these 5 folds. Yes. Okay, so let's have a closer look on what's the remaining error term. Therefore, we compare the errors from the simple model and once the complex model. On the x-axis, we can see the target grain size, and on the y-axis, we can see the predicted grain size. And here, what immediately catches the eye is that for smaller grains, for example, here, the complex model has a much larger spread. But this is mostly due that we have pretty few samples available for this small grain size, which makes it also hard for this model to work well for smaller grains. As well, we have to mention here, which is also a problem, which was a problem during the data collection process from the site from WSL, that the smaller grains are hardly distinguishable between like just recorded noise and the impact of a real grain. So now let's have a closer look on what features had the most impact on our model output. Here on the y-axis, we can see the feature name, and on the x-axis, the Shep value. The Shep value is an approach from game theory, which can be used for explainable AI. And here, the Shep value actually indicates the grain size in millimeter. On the right side, we have a color scale indicating a high feature value, and in gray, a low feature value. So if you now look on the mean spectral roll-off, we can see that when the mean spectral roll-off is high, then we have a strong negative impact on our model output, the grain size. And yeah, this chart showed also that it is very interesting to see that some basic features, which we have also additionally extracted from the raw data signal packages, tend to perform well and had a good impact on the model output. like for example the pack sum, which is the second on top. It's actually just the sum of the absolute amplitudes in a signal package. So how does this look for two particular prediction? One's for a smaller grain and one's for a bigger grain. Here again, we can see on the y-axis the feature name and additionally the actual value of the feature name in gray. And on the x-axis, again, the Shep value indicating the grain size in millimeter in our terms. And here we can see that, again, the mean spectral roll-off is high, and this impacts our model output in a strong negative way, and vice versa, for a larger grain, it impacts our model output in a positive way.
Thank you very much. So now let's move on to the last part from our project, where we compare the different models with different measuring systems. So Simon explained you the simple and the complex model for the CatBoost algorithm, but what we also did is a third one. This was our benchmark model and was for us more like a baseline to compare it, how is it with our final models here. So let's take the focus on the SPG. On the left side, you see that the performance from the simple one and the complex one is really small. You can't literally say a difference between them. But you should know that the amount of data between these two models are huge. For example, the simple one was like just 9 features, and for the complex one was more than 40 features. And yeah, the amount of the features is huge, but the performance is basically the same. So that's an important thing you should know. But at least what we can say about all measuring systems, that the complex model was always a little bit better than the simpler one. And for WSL, it was also really important to know which measuring system is now the best. And also, again, here it is really hard to tell you, because you can see that the difference is really small. But at least we can say, if we have to compare, that the SPS, the complex CatBoost algorithm model, is slightly better than the others, which is a good sign, because this was the approach from the WSL, because as I told you earlier, it is the newest one, and because it is the newest one, they hoped that it would be performed better than the others, and it actually do that, and that's the good thing. So now, finally, what we are hoping, or what WSL is hoping with the models, what we did here. So they hope that they can help to increase the alpine regions, the safety from them, to detect bedload transport events in an early stage and prevent them, so that such images belongs to the past. So that's all from us. I hope we could give you a good insight in our project, and if any questions open, go ahead.
Thank you very much, Firat and Simon. We have some questions already. Now we have 5 minutes for questions, and Gabriel needs to come to you with a microphone so that our viewers online can hear you as well.
Let's want the question part.
Hi, thank you for the presentation. I was just wondering, did you test your model when you have different sizes at the same time? Because in a river, you probably have a whole distribution of this. Were your experiments always with the same size, or did you also had data for mixtures of different sizes of grain?
Okay, first we have to mention that the data collection process was made by the WSL, and during the data collection process, they put through grains one by one, so that they can make sure that this is actually this grain which impacted on the sensor plate. And the evaluation on the field measuring, it's a little bit else. So what you're trying to make here is that you try to model the mass which is transported in a river to the total mass. But this is also the evaluation part which is being done now from the WSL is also, not from us.
Thanks.
More questions? There's one here in front.
So you build your model specifically for WSL. I was wondering if you can see some industrial applications where you can use the same setup, like use acoustic signal to predict that-size particles?
I think we cannot use these models for like other domains because it was trained specific on these grain size data. Yeah, perhaps there might be a case in the future where you can use it, but I think in this state it's not possible yet.
So we are using acoustic signals, and I guess underwater the acoustic behaves totally different than in an air environment. So it's, I guess, really hard to compare it with another case.
And these are also, we have different measuring system, which all they have some characteristics, how they measure these grain impacts. And yeah, I think these models are specifically for these kind of measuring systems.
This question brought more questions.
Thank you for the interesting talk. I was wondering in one of the last slides, I think I misunderstood, but it's just a question of clarification. So the purpose was to compare between different measuring systems.
You mean this slide?
Yes. Did you extract your features always from only one of them, or did you mix features from the 3 measuring systems in your models?
So we have here 3 different models, and so we never mixed any other models together. No.
And the features from different measuring systems were never mixed together because the purpose was explicitly to imagine you only have one of them.
So
at a
we
time,
have.
or
Sorry. Yeah. So we have features which are in all 3 models implemented. So they have like same features, but what the complex model has is a lot of more features. They have the features from the simple one, but a lot of more different features too.
no, maybe my question was not clear. You have these 3 measuring systems, SPG, SPS, and MPA. And when you extracted these 44 features, some of them came from the one system, some of them from the second, and some of them for the third, or they were all extracted from one system?
No, they were all extracted from for each measuring system.
Yes.
Separately?
Separately.
Yeah, separately.
Okay. But you always reproduce the same features just from okay.
Exactly, yeah.
Yeah.
Because if you imagine the artificial flume where the sensors are installed, they are like installed next to each other. So if one grain is being put through this artificial flume, then this grain will probably hit all of them in a
Yeah, you could also think of combining 2 measuring systems.
Yeah.
This was
But this is not our approach.
one of the business ideas
No.
to combine 2 or 3.
Yeah.
No, this isn't.
Okay. Good.
One final question, maybe?
Yeah, I was wondering if you had considered different nature of grains, like in a region where you have more like limestone bedrock, or in a region where you have more like, I don't know, quartz bedrock, or if this doesn't influence your models.
This wasn't like directly the approach from WSL because they have this natural environment station on particular exactly the regions where they know which kind of stones are going through that. So no, we just have like the size in millimeter. We didn't calculate the mass of them, for example.
Okay. Thank you very much, Firat and Simon. Very important mission that you're on.